The Webb look is so far out that getting light has been journeying for more than 13 billion years. However, the universe has been broadening, and consequently, the light has been reaching out for the most far-off universes. We're thinking back in time, almost to the Big Bang. The hugeness of the universe could appear huge, yet every single piece of it began from what we insinuate as the singularity. At this point, this is how we could decipher the Big Bang theory. At any rate, the James Webb Space Telescope, JWST, has uncovered huge secrets about the birth and advancement of the universe, leaving us puzzled. Esteemed physicist Brian Cox has broadcasted that the vital discoveries made by the JWST may, all things considered, reshape how we might interpret the universe as a whole. Join us as we plunge into these new eminent disclosures that promise to change our perception. The James Webb Space Telescope, named after the recognized NASA chief James E. Webb, remains as a marvel in current scientific examination. This telescope represents a gigantic mechanical leap forward from its predecessor, the Hubble Space Telescope, occurring as a result of a helpful effort between NASA, the European Space Agency, and the Canadian Space Agency. The JWST outperforms the capacities of its predecessor. It uses cutting-edge technology and a design optimized for focusing on the universe in remarkable detail. Not like the Hubble, the JWST conveys clear and sharp pictures of faraway grand bodies, working primarily in the infrared range. This intriguing part allows it to penetrate cosmic dust and capture heavenly objects that were previously hidden away from our view. With its beast's 6.5-meter primary mirror made from 18 hexagonal segments, the JWST dwarfs the Hubble's reflector size. Positioned around 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in a condition of congruity with Earth, ensuring a consistent and persistent perspective on the universe. While investigating the faraway corners of the universe, it includes not just investigating light years, but also time travel. The JWST uses infrared instruments to detect great objects and events dating back billions of years. The light produced by these objects, as a result of the expanding universe, goes through redshift, moving from the visible range to the infrared frequency or longer. Fortunately, the JWST can detect infrared light emitted by distant bodies at extreme distances, enabling analysts to study the formation of stars, examine astronomical system development, and inspect exoplanet atmospheres. Its most recent remarkable discovery involves identifying an immense mass of astronomical systems at the edge of the perceivable universe. This finding challenges the validity of the theory of how things became, prompting a reassessment of our key cosmological assumptions to better understand how we arrived. To comprehend how we arrived here, we should take a short trip through the history of space exploration. Early civilizations like the Greeks and Chinese established the groundwork for understanding planetary development by observing heavenly bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. During the 20th century, Edwin Hubble, an influential space expert, made notable discoveries in cosmology and observational space science. His observations uncovered that faraway nebulae were isolated universes long past the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law, laid out by him, showed that galaxies farther away were moving away at higher rates, providing evidence for the expansion of the universe. The post-World War II history of space exploration marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital journey in 1961, and the Apollo 11 moon landing in 1969 as key milestones. Fast forward to 1990, when the Hubble Space Telescope was launched, providing extraordinary clarity and stunning insights into the universe. The journey from ancient observations to the technological marvels of the James Webb Space Telescope highlights the ongoing advancement in our ability to interpret the universe. The Hubble Space Telescope, for example, captured the famous Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by massive columns of gas and dust. Another key achievement was the Hubble Deep Field, capturing an immense number of galaxies in what seemed like a void patch of space. The HST also delved into exoplanet atmospheres, pinpointing elements like water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. Following the discovery of the nearest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These accomplishments established the Hubble Space Telescope's legacy as a cornerstone of modern cosmology, astounding the world with its staggering, enormous discoveries. Its successor, the James Webb Space Telescope, was launched to build on the technological advances and lessons gained from our understanding of the universe's beginnings, which today is explained by the prevailing theory of the universe's origin around 13.8 billion years ago. The universe began as a hot and dense singularity, rapidly expanding and leading to matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of molecules, stars, galaxies, and the various structures observed today. The Big Bang Theory also explains the cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite being widely accepted, the theory of how things came to be faced skepticism and challenges in its early days. Alternative models, like the steady-state theory, proposed a universe without a particular beginning, and concerns about evidence supporting the initial singularity, expansion, and observed anomalies emerged. Most of these objections were addressed over time. A critical piece of evidence came with the discovery of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, alongside technological advancements, further supported the theory. Exact measurements of cosmic microwave background radiation closely match theoretical predictions. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can peer through cosmic dust. The JWST, working primarily in the infrared range, captures the oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared capabilities allow it to focus on star-forming regions, stellar nurseries, and the formation of stars hidden from optical telescopes. Infrared light, with longer wavelengths compared to visible light, can penetrate interstellar dust, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects, primarily emitting in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As galaxies move away, their emitted light waves get stretched, causing a shift toward longer wavelengths, redshift. The JWST's infrared capabilities can detect these redshifted signals, capturing light from the early universe and offering insights into its formation and evolution. Energetic events, like black hole mergers or new star births, predominantly release energy in the infrared range. The discovery of such ancient galaxies at the edge of the observable universe challenges current models of galaxy formation. These findings suggest that galaxies may have formed much earlier than previously thought, forcing scientists to reassess the conditions that allowed for such rapid development in the early universe. This realization opens new avenues for research into the formation of the first galaxies, stars, and black holes, potentially revealing unknown aspects of cosmic history. In addition to unveiling these early cosmic structures, the JWST has also provided valuable insights into the chemical composition of distant exoplanets. By analyzing the atmospheres of exoplanets, it has detected trace elements such as water vapor, methane, and carbon dioxide, key ingredients for life as we understand it. These discoveries are essential for the ongoing search for habitable worlds outside our solar system and could have profound implications for our understanding of life's potential beyond Earth. The JWST's ability to look deeper into space and further back in time allows it to study the earliest stages of cosmic evolution, offering a clearer picture of how the universe began and evolved. The telescope's infrared capabilities are critical for investigating objects obscured by dust, allowing scientists to peer into regions of space where star formation is occurring or where black holes are feeding. These observations are crucial for expanding our understanding of fundamental astrophysical processes, such as the birth and death of stars, the formation of galaxies, and the behavior of dark matter and dark energy. Moreover, The JWST's discoveries extend beyond just the distant past. It is also uncovering present-day cosmic phenomena that were previously unobservable. For example, the telescope has captured stunning images of cosmic collisions, galaxy mergers, and the intricate dance of gravitational forces that shape the universe. By studying these processes, scientists can gain a better understanding of how galaxies and stars evolve over time and how the universe continues to change. As the JWST continues to explore the cosmos, its discoveries will undoubtedly reshape our understanding of the universe in ways we can only begin to imagine. By providing new insights into the origins and evolution of the universe, the telescope is not only advancing our knowledge of the cosmos, but also opening up new possibilities for future scientific exploration. The mysteries of the universe are vast, and with each new discovery made by the JWST, we move one step closer to unraveling them. Ultimately, the James Webb Space Telescope is poised to be one of the most transformative tools in the history of astronomy. It promises to provide answers to some of the most profound questions humanity has ever asked. How did the universe begin? How do galaxies, stars, and planets form? Are we alone in the cosmos? As it continues its mission, the JWST will continue to push the boundaries of human knowledge, uncovering the secrets of the universe and inspiring generations of scientists, engineers, and explorers to look up at the stars and wonder about the vastness of space and our place within it. We can acquire bits of knowledge into how universes, stars, and planetary frameworks emerged and advanced over billions of years. These perceptions, too, add to more extensive inquiries concerning the basic nature of the universe, counting its arrangement, structure, and the forces governing its development. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its fundamental constraint was its failure to penetrate successfully vast dust and distinguish the infrared light emitted by ancient worlds. Older telescopes depended on visible and ultraviolet light observations, making it challenging to investigate the early universe, where these frequencies are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope, JWST, represents a significant leap forward in observing galaxies from the universe's early stages. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang, utilizing its infrared sensitivity and advanced imaging capabilities. The JWST has revealed a wealth of ancient galaxies, offering remarkable clarity and detail in understanding the universe's transformative history. Preliminary results from JWST observations have stirred waves in established cosmological models. The detailed data challenges several aspects of prevailing theories, prompting cosmologists to reconsider fundamental principles governing how we understand infinite evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense discussions within the academic community. JWST observations have uncovered more galaxies in the early universe than expected by existing models, suggesting a more complex and rapid evolution process. Some observed early galaxies appear more evolved than anticipated, challenging traditional models that predicted slower development. The discovery of an immense mass of galaxies challenges the accepted distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than previously thought. These observations raise intriguing questions and avenues for further investigation. The presence of large structures challenges early models of cosmic construction and arrangement, inciting scientists to refine models for a better explanation. Understanding how such massive structures assembled quickly after the Big Bang presents a puzzle that requires an explanation that doesn't violate fundamental principles of cosmology. Significant differences in the conditions of the early universe, compared with forecasts based on existing models, have also been revealed. These differences could suggest previously obscure physical processes, unforeseen circumstances, or unidentified astronomical anomalies. In simple terms, these variations have prompted scientists to reevaluate and improve our models of the universe. Right now, there's no option but to say that further investigation is needed to consolidate these remarkable observations into a more comprehensive understanding of the universe. Initial observations often provide exciting glimpses into the universe, but in-depth analysis sometimes uncovers contrasts. For instance, early observations might show specific properties or arrangements within distant galaxies that, upon closer inspection, reveal variations in their composition, structure, or evolutionary pathways. In conclusion, massive anomalies are undoubtedly complex and require careful examination for us to accurately understand their true nature. Spectroscopy, a technique that uncovers the properties and history of celestial objects, is an example. It involves analyzing the light emitted or absorbed by astronomical objects. By studying the properties of light, spectroscopy provides detailed information about the chemical composition, temperature, density, and motion of celestial bodies. This analysis helps us understand the origins, evolution, and contributions of celestial bodies to the cosmic fabric. The JWST has uncovered several cases where initial observations differed from later examinations. For example, initial observations of distant galaxies suggested a simple structure, primarily dominated by lighter elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic analysis using the JWST showed fascinating variations in chemical signatures, identifying heavier elements or compounds previously undetected or misjudged in the early universe. This challenges conventional ideas about the early universe's composition and the processes responsible for their formation and spread across vast distances. Similarly, initial assumptions about galaxies in the early universe were based on preliminary observations, suggesting a relatively uniform pattern of development and organization. However, more detailed studies by the JWST uncovered a much more diverse and complex array of chemical compositions within these galaxies. The James Webb Space Telescope, JWST, continues to amaze the scientific community with its exceptional capabilities. As it delves further into the universe, it is not only expanding our knowledge of distant galaxies, but also revealing new phenomena that challenge established ideas about the evolution and development of the universe. One especially captivating aspect of the JWST's work is its role in studying the birth and death cycles of stars. By observing these cycles in greater detail, astronomers can study the life cycles of stars that were previously too distant. The telescope's infrared technology is crucial in this area. Stars often form within dense clouds of gas and dust, which can obscure them from visible light telescopes like Hubble. However, the JWST's ability to detect infrared light allows it to peer through these clouds, offering a clear view of star-forming regions. This capability helps scientists track how stars are born, evolve, and ultimately die, providing insights into the materials that are ejected into space during celestial deaths. These materials, including heavier elements like carbon and oxygen, are essential to the formation of planets and other celestial bodies. Moreover, the JWST is investigating the nature of supermassive black holes, which reside at the centers of most galaxies. These mysterious objects are believed to play a critical role in the formation and development of galaxies. The telescope's ability to observe the infrared spectrum is helping astronomers uncover the mechanisms behind black holes. For example, they influence surrounding stars' gas and dust. This research is contributing to our understanding of how galaxies evolve and change over time, especially in the early stages of the universe. Another remarkable feature of the JWST is its ability to study exoplanets. By analyzing the atmospheres of distant worlds, scientists hope to detect signs of habitability, such as the presence of water, organic molecules, or even indications of life. These discoveries could have significant implications for the search for extraterrestrial life, offering new insights into the conditions that make a planet suitable for life.